Without semiconductors, nothing runs. And I say without lithography, no chips are being made. When you finish your machine, the machine has the next destiny.
Right.
The worst thing you happen, you're spending all your money in making a machine that sits there and nobody believes it works. Theoretically, there was always a crossover.
But that was much later than you originally...
About 8 years later than we promised.
Right, so you were in that journey, these 8 years, you were never like, oh, this is not going to work at all. Should we stop it?
No. A new material has usually been a revolution for our customers. Don't try to sell things to customers which doesn't provide value. Don't even try. Think about your value proposition to your customers and how you scale that.
Yes.
And if you don't see something scales, you cannot spend the money. And that often requires you to have a broader view on the problem than you probably would have from an AI perspective.
I'm privileged to be here today in Amsterdam to speak with Martin van den Brink about the relationship between AI and semiconductors. He was the CTO and president of ASML. Welcome, Martin van den Brink. Could you introduce to the audience what lithography is?
Yeah, lithography is I would say in general terms printing, but maybe you mean to say lithography and semiconductor. Which is you printing the pattern on a silicon wafer, which been used in subsequent processes to connect and create a semiconductor chip.
And so in the beginning, ASML made a few big bets on what technology to develop.
The whole semiconductor world at the time, and to some extent still is, governed by what we call Moore's law. Every 2 years you scale down the chips. So with the same chip size, you could afford 2x the times of transistors. So the scaling law has been governing our destiny. When I joined the company, Philips was engaged in both e-beam technology as well optical. And the state-of-the-art resolution at the time was 1.5 micron lines. And the general consensus at the time was everything below 1 micron is e-beam. And here we are still. Not with 1 micron, not with a tenth of a micron, but now we are doing a fraction of a tenth of a nanometer.
It sounds almost impossible to me, but is there a time, do you think, where Moore's law will actually stop?
I don't think we will be the end of Moore's law the next 10 to 20 years. The slowing down of the shrink rate will still push the increased system integration of chips. Well, the next 10 years there'll be increasing amount of 3D stacking of chips.
So what kind of materials or what kind of problems do we need to solve with new materials as we are moving into this third dimension?
One of the limitations in 3D stacking, you have to get the heat out of the cube, which is way more difficult than a two-dimensional structure.
Yes.
But also require a careful 3D design.
Yes.
Allowing high dissipation areas to dissipate and control the heat, as well as materials to get the heat out. I think to be fair on the history and the role of stage development, we have become world-class on fast stage and servo control. And in the beginning, we had just complete analog control. Since then, we moved everything to digital control and computer control and simulation. And we have been able to get extremely well in that stuff.
And then, of course, there was also the transition to extreme ultraviolet light. That was actually a big bet. I think you even said to Peter Wannick at that point, if we don't do this, we will be done or we will not survive.
Yeah.
So can you tell us whether it was extremely difficult on the technology side, or was it more sort of a commercial decision that was very hard?
I was asked to get a 10-year plan for lithography, and my plan was going from the then existing I-line down to EUV. And as a result, we put 3 technologies together. Comparison was E-beam, ion beam, and EUV. So we all believed, and it was very clear by that, making lines smaller, give you the profits to pay for it. So the only question is which one will do it. And then the difference between EUV and ion beam and E-beam was charged particles or photons. There was a fundamental limit in charged particle optics was the particle-particle interaction. And the only way to get a good image is slowing the productivity down. So we choose that the only way we make money is get high productivity EUV.
So did you always know that this was going to succeed, or was this also, even on the technology level, a big bet for you?
First of all, we didn't spend huge amount of money on EUV in the early days. And we focused all of our money on progressing what we have. And it was so successful that when we proposed EUV to customers, their view was EUV was too expensive. So the future without EUV was very simple. You will sell more of your existing technology than you would ever sell with EUV. And the cumulative cost of our customers would reach a level where we were concerned that the cost of litho would stop our customer to shrink. So hence we made EUV not necessarily to be more successful in litho, which we already were, but to make sure that the cost of our customers are low enough to continue to motivate them to shrink. And then over time, the transition to EUV was quite natural. At the point, some customers need up to 10 exposures for exposing one layer. Then you replace the whole thing with one exposure in EUV. That's how the economics works.
But even the technology must have been also a difficult journey, because
That's correct.
I remember, you promised something at some time and it took many years to actually deliver.
It's about 8 years later than we promised.
Right, so you were in that journey, these 8 years, you were never like, oh, this is not going to work at all. Should we stop it?
No.
How do you deal with the uncertainty?
Now, first of all, we need to be cheaper than the alternative.
Mm-hmm.
And every year you wait, the alternative gets more expensive. So theoretically, there was always a crossover. We already knew we could have good imaging. And this was just fundamental physics. The economics didn't add up. So we have taken more time to get the economics right of EUV, but it was never a super hard showstopper.
So some people say that the EUV machine is the most complex system in the world. And designing a very complex system comes with many challenges. If you create too many dependencies, if you fail one thing, the whole thing may come down. What was your way of dealing with these incredibly complex systems?
When I joined, you start scaling up the groups beyond 100 people, 250 people, 500 people. And very quickly, we had an issue on how you break the complexity in pieces. So we cut the problem into pieces, and you have very clear interface specifications. So those teams are to show a working stage, a working handling system, a working alignment system before you start integrating. We have learned throughout the company to deal with high level of complexity.
But do you think there's an end to this, or can we still make things way more complex?
There is no end on simplifying things.
But also in making things, systems that are naturally even more complex. I mean, if you think of our bodies, they are incredibly complex.
Yes, so I personally think the system engineering concept can be able to deal with that, as long as on every single level, the people involved understand what they're doing and has enough understanding they can integrate it. And as long as you have your system integrity maintained, which is important. If you screw up that integrity of the system, you cannot integrate. So that's extremely important.
Mm-mm. And do you think that AI can play a role in managing this complexity? Because you can think of an AI system as a system that can become much more intelligent than a human in the future. It can have access to much more data. So you could argue maybe that an AI system could design the lithography machines of the future. These might be very differently organized than we design them today. But do you think that's something that will have a future, or this is maybe something we are overestimating?
Well, I would be more down to earth. I'm not go as far as you said. I don't exclude it either. But today, what would help if we could use AI to help us designing systems. And we do that today.
So maybe going back to the role of AI in the sciences. Right? So in weather prediction, the meteorologists have been very good at storing a huge amount of data. There's petabytes of weather data available. And we have very large supercomputers predict the weather for us by basically solving the physics equations. These are Navier-Stokes equations that we know the physics and we can solve them, but it's very expensive. So the machine learners have now trained what we call surrogates that have basically gotten rid of all the physics. It's just a massive set of transformers, neural networks that predict the future state of the weather. And even though the meteorologists were very, very skeptical when this was started, these machine learning models could predict the weather, let's say, 10 days ahead, better than the numerical solvers, but at a fraction of the cost, like 10,000 times faster. And so here we see an example of where we completely ignore the physics. We have no clue what's happening, how this machine actually predicts the weather, but we can verify that it actually does predict the weather very well. The most important point is, do we even want systems that we don't understand anymore? Even though they make perfect predictions, if we don't know how they make the predictions, are they still of value to us? If you talk to a scientist, they typically say no, but there might be different kinds of problems. Like at CuspAI, we predict materials. If we create a magic black box that would give me the materials with all the properties that I desire, and I don't know how it did it, but it comes out, and I can verify it has the right properties, should I accept that, yes or no? Is this a valuable system, yes or no?
If you like to be good at something like materials, like your own objective, you will not be successful without having expert knowledge on materials.
I agree.
I'm convinced about it.
Yeah, I actually agree with you. I'm just...
Okay.
you
have to push me on the edge.
Yes, at CUSP we do have a lot of chemists and material scientists.
Correct.
Exactly because we think that we need the domain experts. So we have contracts with different universities and other research institutions, but also with customers who have lab capability, with whom we deeply partner so that they can do the experiment and we will sort of do the digital part and we connect the two. This keeps the CUSP platform broadly applicable and we don't sort of commit or lock ourselves into one single vertical. And I also understand that ASML went through a journey of deep partnerships with, for instance, Zeiss, but also with your customers to have them involved in the actual financing of the next generation of EUV machines. And how do you look at partnerships in an ecosystem of suppliers?
What we have done almost throughout our whole life, we try to sell the equipment before we have it, making sure when you finish your machine, the machine has the next destiny. Right. The worst thing you happen, you're spending all your money in making a machine that sits there and nobody believes it works. So we try to lock in customers before it happens. Yeah. It happens from day one. Philips was at the time the first set of machines committing themselves to X amount of machines before the machines exists. That process continues. At some point in time with immersion and 157 nanometer, we require customers to give advance payment to get skin in the game. And in the case of EUV, we're ending up even with customers taking a stake in ASML in exchange for R&D money to be spent on EUV. And it's all important to make sure that you don't have a customer which is not willing to pull your solution out of your hand. You need to have a customer eager to pull the solution into his fab.
Yeah.
And then after that point, still continue to work with the customer to make it really work. Building up a mutual trust for each other capability, which is also the basis of the next round of new equipment.
And so how many new materials are introduced in this field, let's say, every year or every node?
I think at least a new material every generation comes out. So there's a lot of work with customers to qualify the material, making sure it's compatible with the processing. That's why a new material is usually been a revolution for our customers.
And so do you think that maybe here AI or CuspAI could actually play a role in designing these materials more efficiently?
These cycles of learning by change the material composition, change the material, looking to the effect.
Yes.
It leads to, if you need to have, let's say, sometimes 100 cycles of learning or so to get from A to B. If your AI can reduce that cycles of learning by half or even more, and can be more precise, limiting your physical experimentation space, yes, that would create a lot of efficiency and value for both the equipment supplier as well as for the customer.
Predicting which experiments one needs to do in order to iterate as quickly as possible to the material that you want. So it could cut the cost, let's say, on experiments that you need to do.
Now, there are various ways of predicting. You can predict more accurately what you need to do, but you also could cut off immediately upfront experiments which will likely not add much value.
I want to thank you for this conversation and taking the time, and hopefully we can enjoy more of your advice at CuspAI over the next years.
Thank you.
Thank you.